Welcome to this lecture on AI and machine learning, where we'll move from core concepts to real-world impact. In the next few minutes, I'll guide you through the main paradigms, modeling choices, evaluation metrics, and practical deployment patterns that matter for business and society, so you can see how technical ideas translate into measurable outcomes and trustworthy applications. This page contrasts the four main learning paradigms. Supervised methods learn from labeled examples to predict outcomes. Unsupervised methods discover hidden structure without labels. Semi-supervised approaches blend small labeled sets with abundant unlabeled data to boost performance. And reinforcement learning optimizes actions through trial and error for long-term reward, each aimed at different business goals from forecasting to anomaly detection. Here we compare regression techniques and tree-based models. Linear and logistic regression handle numeric and binary prediction with simple, interpretable relationships, while decision trees give clear rules and feature importance. Random forests combine many trees to improve accuracy at the cost of some interpretability. So teams must balance explainability against predictive power when choosing the right model for the task. This slide explains neural networks and deep learning as stacks of simple processing units that automatically extract hierarchical features from raw data. By layering neurons and using backpropagation to adjust weights, deep networks learn complex patterns useful for image recognition, speech processing, and language understanding, enabling breakthroughs in perception and representation that reduce manual feature engineering. Data splitting and overfitting are critical practical issues. We partition data into training, validation, and test sets to tune models and evaluate generalization. Watch out for overfitting where a model memorizes noise rather than patterns, and use metrics beyond accuracy, like precision, recall, and F1, to measure real-world robustness and align models with business priorities. Choosing evaluation metrics changes decisions and stakeholder trust. Accuracy gives a simple correctness number. ROC-all-Z measures discrimination across thresholds, and confusion matrix-derived metrics like precision or recall let you prioritize false positive or false negative costs. Linking metric choice to business impact is essential because the metric you optimize directly shapes operational risk and user confidence. In finance, AI drives several real-world applications. Real-time anomaly detection flags suspicious transactions instantly to prevent fraud. Credit risk models expand assessment using alternative data for fairer lending, and reinforcement learning agents can execute high-speed trading strategies that react to market microsignals, all aimed at reducing loss, widening inclusion, and improving operational efficiency. Healthcare applications include convolutional networks that analyze medical scans for automated anomaly detection, predictive rostering models that forecast admissions and optimize staff schedules to reduce burnout, and personalized dosage engines that tailor treatments based on patient profiles and genetics, together improving diagnostic accuracy, operational efficiency, and clinical outcomes. This overview highlights three key applications. Autonomous vehicles fuse camera, LiDAR, and radar into a unified perception model for safer decision-making. Fleet management uses telemetry and anomaly detection to predict failures and reduce downtime, and collaborative filtering recommenders analyze user interactions to suggest relevant products, boosting engagement and revenue with personalized experiences. Advanced topics cover transformer architectures that capture long-range dependencies through attention mechanisms, generative design, and self-supervised pre-training that cut labeled data needs by learning from unlabeled corpora, and the growing compute and carbon costs as model scale increases, reminding us that technical progress must be balanced with data efficiency and environmental responsibility. Ethical AI requires addressing bias in data, building explainability into models to meet regulatory and public expectations, enforcing privacy and compliance practices for data, sovereignty, and user consent, and proactively managing long-term risks from powerful systems. Only a combination of technical rigor and ethical oversight can sustain public trust in AI applications. Finally, a practical implementation path is to start with small, supervised pilots to dev-risk high-value use cases, iterate continuously on metrics tied to business outcomes, foster cross-disciplinary teams that break down silos, and commit to lifelong learning so your organization adapts as algorithms, data, and hardware evolve rapidly.